Okay, let's jump into this stack. We're looking at something pretty fundamental today, aren't we? Thinking about, big structures, skyscrapers, pipelines, bridges.
Yeah, the things holding them together, welded joints. And the question is, how do we know they're actually safe, strong enough?
Exactly.
Mm.
And that's where this whole idea of destructive testing comes in, which sounds, well, traumatic.
It kind of is. The sources we have dig right into it. You're literally breaking samples of welds, but in very controlled ways. It's all about getting crucial information.
Right. So that's our mission for this deep dive.
Oh.
Unpack what destructive testing really means, why it's so vital, especially for, qualifying the welding procedures before the real work starts, and explore the specific ways engineers do this, deliberately breaking metal.
It sounds counterintuitive, maybe, but it's essential. These sources show how experts pull, bend, smack, even try to crack open welded pieces. It's this rigorous checking that guarantees quality and safety.
The hidden work behind the structures we see every day.
Precisely. It builds confidence.
So let's get into why breaking things carefully is the key to making things that don't break unexpectedly.
Okay, so the why first. The sources are really clear. This isn't just a nice to have in many cases. European Welding Standards, for example, they flat out require it for qualifying a welding procedure.
Meaning, before you can use a certain welding method with specific materials on a real job,
You've got to prove it works. Prove it makes sound, reliable joints. You weld a test piece, check it non-destructively maybe, and
then you cut it up and break the pieces. That's the destructive part. You sacrifice the sample to learn about the process.
Exactly. And these tests, they fall into sort of two main camps. You've got your quantitative tests. Think numbers.
Measurements.
Right. Measuring a specific mechanical property like how strong is it? How hard is it? How much energy can it absorb before it snaps? You get a value.
Okay, like tensile strengths or impact toughness.
Yeah, those are key examples. Tensile tests, impact tests, hardness, even something called CTOD testing. And then the other camp.
Qualitative.
Qualitative, yeah. These aren't about getting a specific number. They're more about judging the overall, let's say, quality or soundness. Are there hidden flaws? Did the metal fuse properly when you bend it?
So more visual checking for defects?
That's a good way to put it. Things like bend tests, looking closely at a polished cross-section that's macroscopic examination, and some simpler fracture tests where you break it open and just look.
Got it. And there's a really important link back to the design stage, isn't there? Something the sources highlight.
Oh, absolutely crucial. See, the engineers designing the structure, they base their calculations on the properties of the original metal, the plates, the pipes, whatever's being joined. They assume the weld you put in is, well, no worse than that base metal.
Hopefully just as good, or maybe even better sometimes.
Ideally, yes. But the design usually relies on it being at least as good. So these quantitative tests, the ones giving us numbers for strength and stuff, they're fundamentally there to check that assumption, to prove the weld meets the minimum properties the whole design depends on.
Ah, okay. So the tests are basically validating the engineer's starting point. That makes sense. Let's dig into those quantitative tests then. Pulling things apart sounds like a good place to start. Transverse tensile tests.
Right. The transverse tensile test. The main goal here is to show the strength of the whole joint weld, heat-affected zone, base metal nearby is up to scratch. You're pulling across the weld.
So you take a piece of the welded plate, machine it into a sort of standard shape, smooth off the extra weld bead on top.
Yep. Remove the excess weld metal. And if it's a really thick piece of metal you welded, you might need to take several test strips from different decks. You see that shown in the source material, the typical test piece shape.
Okay. And then into the pulling machine.
Exactly. A tensile testing machine grips both ends and just applies a steadily increasing pulling force until snap. It breaks.
And you measure the maximum force it took?
Max force,
Well,
right.
yeah.
And the original cross-sectional area of that test piece.
Yeah.
Divide the force by the area, and that gives you the tensile strength, the stress it could handle.
How do you know if that number is good enough? What's the pass-fail?
Ah, the acceptance criteria. Typically, if the break happens in the weld metal itself, it passes if the strength value is equal to or greater than the minimum tensile strength specified for the base material.
So the weld has to be at least as strong as the metal it's joining.
Pretty much. Though interestingly, some standards, like ASME IX mentioned in the sources, have a slightly different take. They might allow a break outside the weld, in the base metal near the weld, as long as the strength is still really high, say, above 95% of the base metal's minimum required strength.
Why would that be okay?
The thinking is, well, if it broke in the base metal, the weld itself must have actually been stronger than that point, right? It forced the failure to happen elsewhere.
Clever. Okay, so that's testing the whole joint strength across the weld. But sometimes you need to know about just the weld metal itself.
Precisely. And that's where the all-weld metal tensile test, or just all-weld tensile, comes in. Here, the goal is different. It's about measuring the property's strength, yield point, ductility of only the deposited weld metal.
Why isolate just the weld metal like that?
Well, a couple of reasons. Welding consumable manufacturers use this test a lot to check their filler wires or electrodes meet specs. But it's also really important for designs that operate at high temperatures. In those cases, the specific behavior of the weld metal itself becomes critical for calculations, not just the overall joint strength.
Right. So how do you prepare a sample that's only weld metal? That sounds tricky.
You typically build up a pad of weld metal or machine it carefully from the center of a butt weld, making sure the test piece is oriented along the length of the weld. The key is the gauge length. The part you actually measure has to be 100% weld metal. The diagrams in the sources show this pretty clearly.
Okay, makes sense. And then you pulled this one too.
Yep, pull it till it breaks. But with this test, you usually use a sensitive measuring device called an extensometer clipped right onto that gauge length.
Why the extensometer?
Because it lets you precisely measure how much the weld metal stretches for a given load. This is how you determine the yield strength, that point where it starts to form permanently. Or, for some materials that don't have a sharp yield point, something called the proof stress. The load extension curves shown in the material illustrate this difference.
Ah, okay. And you mentioned ductility earlier. That's measured here too.
Yes, very important. Ductility tells you how much the metal can stretch or deform before it actually fractures. We measure it two main ways in this test. First, the percentage elongation, basically, how much that gauge length stretched compared to its original length. And second, the percentage reduction of area, how much the cross-section necked down or got smaller right where it broke.
And high ductility is generally good, means it's less likely to just snap.
Generally, yes. Ductility allows the material to absorb energy and deform under stress, which can prevent sudden, brittle failures. It's a key property.
Okay, fascinating. We've pulled them apart sideways and lengthways. What other ways do we test these welds quantitatively?
Next big one is toughness, specifically resistance to brittle fracture. And the workhorse test for this is the Charpy V-notch impact test.
Brittle fracture, that definitely sounds like something you want to avoid.
Absolutely. It's a major concern, especially for structures operating in cold environments or subjected to sudden impacts. A material could be perfectly strong if you pull it slowly, but if it lacks toughness, especially when cold, a small defect could cause it to fracture suddenly, catastrophically, with almost no warning. Think snapping like glass versus bending like taffy.
Right, and temperature is a big factor here.
Huge. Many common steels, like carbon manganese steels, go through a transition. They can be quite ductile and tough at room temperature, but get significantly more brittle as the temperature drops. Our sources show that classic S-shaped curve, the ductile to brittle transition temperature graph. Toughness just plummets.
So you need to test it at the right temperature.
Exactly. The Charpy test is often done at a temperature related to the lowest temperature the component is expected to see in service. You have to ensure it has enough toughness at that temperature.
So how does the Charpy test actually work? What's the setup?
You use small, standardized rectangular bar specimens. The most common is 10 by 55 millimeters long. And crucially, it has a specific V-shaped notch machined into one face.
A V-notch. Why the notch?
The notch acts as a stress concentrator. It provides a defined point for the fracture to start, mimicking how a small flaw or sharp corner might behave in a real structure. And where you put that notch is critical.
Where do they usually put it?
Typically, right in the center of the weld metal, but also, very importantly, at different locations within the heat-affected zone, the HAZ, that area base metal right next to the weld that got heated but didn't melt. Sometimes the HAZ can actually be the area with the lowest toughness. The diagrams show these typical notch locations.
Okay, got the notch bar, then what?
Then you hit it, but in a very controlled way. You cool the specimens down to the specified test temperature. Then you quickly take one out, place it on supports in the Charpy testing machine with the notch facing away from where it's going to get hit. A heavy pendulum hammer swings down, strikes the specimen on the face opposite the notch, breaks it, and swings up the other side.
And you measure how much energy the pendulum lost.
Exactly. The machine measures the difference in the pendulum swing height before and after breaking the specimen. That difference corresponds to the energy absorbed by the specimen during fracture, usually measured in joules. More energy absorbed means higher toughness.
Simple concept.
It is, but effective. And because there can be some scatter in the results, especially with welds, you always test at least 3 specimens for each condition, each location and temperature, and report the average energy value.
And that average has to meet some minimum requirement.
Yep. The relevant standard or the client specification will state a minimum average absorbed energy required, say 27 joules, or 40 joules at minus 20 degrees C, for example.
Is that all you get from the test, just the energy number?
No, there's more qualitative info too. After the test, you look closely at the broken surfaces of the specimens. You assess the percentage crystallinity or shear fracture appearance. A flat, crystalline-looking surface indicates a brittle fracture, while a dull, fibrous, torn surface indicates a more ductile, tougher fracture.
Ah, so the look of the break tells a story too.
It does. And you also measure lateral expansion. That's how much the specimen widened or bulged out on the sides just behind the notch due to the impact. More bulging means more plastic deformation occurred before fracture, indicating higher toughness. The sources show illustrations of what brittle versus tough broken specimens look like.
Okay, that's quite a lot of information from one little impact test.
Yeah.
What about hardness? We mentioned that earlier.
Right, hardness testing. This measures the material's resistance to basically being dented, permanent plastic deformation under a concentrated load.
And why is hardness a concern in welds? Is harder always better?
Not necessarily. In fact, excessive hardness, especially in the heat-affected zone of certain types of steel, can be a problem. Very hard microstructures are often less tough and more susceptible to cracking, either during fabrication, like hydrogen cracking, or later in service. So for critical applications, codes often require a hardness survey.
A survey, meaning you test hardness in multiple spots.
Exactly. You take a cross-section of the weld, polish it up nicely, often the same piece you might use for macroscopic examination, and then you make a series of tiny indentations across the weldment.
How do you make the indentations?
Several standard methods exist. Vickers is very common for welds because it uses a tiny diamond pyramid indenter that works well on different hardness levels and leaves a small mark. You press the diamond into the surface with a precise load, say 10 kilograms for a set time. Then you measure the size of the square indentation left behind using a microscope.
And a smaller dent means harder material.
Correct. The hardness value is calculated from the load and the indentation size. Other methods like Rockwell, using a cone, or ball, Brittle, using a larger ball, mostly for base metals, exist too. The key for weld surveys is usually making indents in the base metal at specific points across the HAZ and in the weld metal itself. You follow a pattern, like the one shown in Figure 4.13 in the sources.
To check for any spots that got too hard during welding.
Precisely. You're looking to ensure that no region exceeds a maximum permissible hardness value set by the standard or specification.
And those hardness values have specific codes, don't they? Like HV or HRC?
They do. You'll see things like 240 HV10. That means a Vickers hardness value of 200 measured using a 10-kilogram force load, or maybe 22 HRC, which is a Rockwell hardness reading on the C scale, or 238 HPW for a Brittle test. The letters tell you the method, the number is the value, and sometimes there's extra info about the load or indenter.
Okay. One more quantitative test mentioned, CTOD, crack tip opening displacement. Sounds complicated.
It is a more complex and generally more expensive test than Charpy, but it gives you really valuable information. Well, Charpy gives a relative measure of toughness. CTOD aims to measure the material's fracture toughness as a fundamental property.
Fracture toughness, how is that different?
It feeds directly into engineering fracture mechanics calculations. This allows engineers to do things like determine the relationship between stress, flaw size, and the risk of brittle fracture.
So you can figure out how big a crack needs to be before it becomes dangerous.
Exactly. Or if you find a crack during inspection, CTOD data can help you perform an engineering critical assessment, or ECA, to determine if that specific crack is safe to leave in service, or if it needs repair, or if the structure needs to be taken out of service immediately. It's crucial for fitness for service assessments.
Wow, okay. How do they even measure that?
You need a fairly chunky specimen, usually a rectangular or square bar, cut across the weld. You machine a notch, then a shallow saw cut, and then this is key, you actually create a sharp fatigue crack at the tip of the saw cut.
You deliberately make a crack grow.
Yes, by repeatedly bending the specimen under low load. This creates a very sharp, natural crack tip, which is what you want to test the toughness against. Then you cool the specimen, put it in a test rig, usually in bending, and apply a steadily increasing load.
And you measure how much the crack opens.
Precisely. You attach a special sensor called a clip gauge right across the mouth of the original machine notch. As you apply the bending load, the crack starts to open, and the clip gauge measures this opening displacement very accurately. The sources show a diagram of this setup.
What does the result look like?
You plot the load versus the crack mouth opening. From that data, you calculate the CTOD value, which represents how much the actual tip of the crack opened just before fracture, or at the maximum load if it doesn't break brittly. It's usually measured in millimeters.
And a bigger opening means more toughness.
Generally, yes. A high CTU value indicates the material can tolerate a lot of deformation at the crack tip before failing, suggesting good resistance to brittle fracture. You test several specimens, maybe 3. The result might be a minimum required CTUD value specified by a standard, or the values are used directly in those ECA calculations we talked about.
And you can tell brittle from tough behavior.
Oh yeah. A brittle material might fracture at a low load with very little crack opening. Maybe a CTOD less than, say, 0.1 millimeters. A tough material will show significant crack opening, maybe ductile tearing before final fracture, and could have CTOD values well over 1 millimeter.
Okay, that's a really sophisticated way to understand how a material behaves with a crack present. So that covers the main quantitative tests, right? Measuring properties.
That's the core group, yes. Measuring strength, ductility, impact toughness, hardness, and fracture toughness. Now we can shift to the qualitative tests.
The ones focused more on checking soundness and quality, less on getting a specific number, like bend tests.
Exactly. Bend tests are a classic. They're relatively simple to perform, but very effective at revealing significant defects and demonstrating, visually at least, that the weld has some ductility.
It shows it can bend without snapping.
Right, you're not measuring how much ductility like in the tensile test, but you're confirming it can withstand a certain amount of bending strain, which pulls the outer surface into tension. Any significant flaws like lack of fusion or big pores near that surface tend to open up and become visible.
And the sources mention different types of bend tests, face, root, side.
Yeah, it depends on the joint type and thickness, mainly for butt welds. For thinner plates, you might bend one specimen with the top surface, the face, outwards under tension, that's a face bend. Another with the bottom surface, the root, outwards a root bend. For thicker plates, say over 10 or 12 millimeter, you usually cut slices through the thickness and bend them sideways, testing the entire weld cross-section. That's a side bend.
How do they control the bending? Just bend it by hand.
Oh no, it's controlled, usually guided bend tests. The specimen is placed on supports, and a plunger or former with a specific radius pushes down in the middle, forcing the specimen to bend around that former.
And the radius matters.
Very much so. The diameter of the former is specified by the welding code, and it's related to the material type and its expected ductility. A tougher, more ductile material can be bent around a smaller radius, like maybe 4 times the specimen thickness, 4 without cracking, whereas a less ductile material might need a much larger radius, maybe 10T or more. You typically bend it to a specific angle, often 120 or even 180 degrees.
What are you looking for after bending? What's a pass?
You look closely at the outer surface that was stretched. It has to be sound. That means no significant cracks or open defects. Some codes might allow tiny indications, maybe less than 3 millimeters long, but generally any substantial crack or opening means the test has failed.
Okay. Simple but revealing. What about the fracture tests mentioned? Fillet fracture and nick broke.
These are even more direct, in a way. Their main purpose is literally just to break the weld open, so you can look at the internal fracture surface for flaws.
Just crack it open and peek inside?
Pretty much. You're visually assessing the quality, looking for things like trapped slag, gas pores, or areas where the weld didn't fuse properly to the base metal.
And where are these mainly used? The sources seem to distinguish their use.
Yes. They're primarily used for welder qualification tests, especially under European standards. It's a practical way to check if a welder can lay down a sound bead without major internal flaws. They aren't typically the main tests for qualifying the procedure itself, although sometimes a fillet fracture test might be used as an alternative to a macro examination for procedures.
Okay, how do you prep these for the fillet weld?
You take the test fillet weld, cut it into shorter lengths, maybe 50 millimeters or so. Then you usually machine a little notch along the root of the weld on one side. Then you just apply force hammer it, press it in a vise, whatever it takes to break it through the weld throat, starting from that notch.
And the nick break, that's for butt welds.
Right. For a butt weld nick break, you cut a piece from the weld and then machine notches into the sides, carefully placed, so that when you break it again, usually by hitting it or bending it, the fracture runs right through the center of the weld metal.
And in both cases, you just examine the broken surfaces.
Yep. You look carefully at the fracture faces for any signs of imperfections, Lack of fusion is a big one. Solid inclusions, slag, porosity. The standard you're working to will tell you what type and size of imperfections are acceptable or cause for rejection.
Got it. And lastly, macroscopic examination was mentioned alongside these.
Yes, briefly. Macroscopic examination involves cutting a cross-section through the weld, polishing it smooth, and then etching it with a mild acid.
Etching. Way.
The etching reveals the microstructure. You can clearly see the boundary between the weld metal, the HAZ, and the base metal. You examine it under low magnification, maybe 5x or 10x, looking for the overall weld shape, checking for good fusion at the root and edges, and spotting any internal flaws like pores, cracks, or slag lines.
So it's like a quality snapshot of the weld structure.
Exactly. It's required for procedure qualification under European standards, and often for welder quals too. While you're not breaking it in the same way, you are cutting up the sample, so it fits within this broader destructive testing context in the sources.
And all these different tests, tensile, impact, bend, hardness, CTOD, fracture, macro, they're all formally defined somewhere.
Oh, absolutely.
Yeah.
You don't just make up how to do them. They're governed by detailed international standards, like those from ISO, International Organization for Standardization, or ASTM, American Society for Testing and Materials, often referenced in specific industry or national codes like EN, European norms, or ASME, American Society of Mechanical Engineers. Our sources list several key ISO standards for these methods.
Like the ISO 6892 series for tensile, 901 Sting for impact, 5173 for bends.
Exactly. Those standards specify everything: specimen dimensions, test procedures, how to report results. It ensures tests are done consistently everywhere so the results are reliable and comparable.
Okay, so let's try and pull this all together for you listening. We've walked through this whole array of tests where engineers deliberately break welded joints. Why does understanding this matter?
Well, because it's really the hidden foundation of safety and reliability for so many things we depend on. These tests are how engineers confirm that the welding processes used will actually deliver the performance needed. The strength, the toughness, the basic integrity, they're the proof behind the design.
They're the gatekeepers, ensuring that the connections in that pipeline or that bridge or even parts in your car can handle the stresses they're designed for. They prevent failures.
That's the core purpose, yes, to prevent catastrophic failures by rigorously checking the weakest link, potentially, which is often the joint. It's amazing, really, the lengths they go to, pulling, hitting, bending, cracking, just to build that certainty.
Systematically looking for problems, confirming the numbers, making sure everything is consistent, all by careful destruction.
It's a fascinating process when you think about it.
It really is. So considering this, this intense level of scrutiny, this deliberate breaking of things to ensure integrity, how does knowing about this hidden layer of testing maybe change how you think about the trust we put in the engineered structures all around us? Something to ponder.